Welcome grade 11s, I hope you're all well. I'm going to be teaching you about quadrilaterals and how we're going to apply them to what we've learned about in analytical geometry. Now, much of what I'm going to do at the initial stage here is revising what you learned about the properties of quadrilaterals in grade 10. And in particular, I'm going to talk about the quadrilateral hierarchy and why that's important for us to think about quadrilaterals. And then we're going to apply that type of thinking with a few examples for analytical geometry. All right, so what are we talking about the quadrilateral hierarchy? Well, a hierarchy in this sense is some sort of ranking system from something that's the least important to the most important. So in terms of quadrilaterals, what does it mean for a quadrilateral to be important, or how do we rank quadrilaterals? Well, we rank them from their properties, from having the least amount of properties to having the most amount of properties. So if we think about just a generic quadrilateral, well, that's a shape that doesn't have any particular properties. The interior angles will add up to 360 degrees, but none of the sides are necessarily equal. There's no parallel lines. And so it's not an especially special shape. So what property could we add to a generic quadrilateral? And in geometry, the idea of parallel lines is a very important idea. So if we have one pair of lines that are parallel, well, we call that a trapezium. Now, does the trapezium have any other properties? Okay, so here's my trapezium with a pair of parallel sides, and this shape doesn't have any particular properties that come along with parallel sides apart from having alternate angles. When we talk about the properties of quadrilaterals, we're interested in the sides, or none of the sides are equal. We're interested in the interior angles, or none of the angles are equal. And there's nothing special about the diagonals either. But if we look at this trapezium, we realize that there might be a special trapezium. A special trapezium that we called an isosceles trapezium. Okay, so we've made a pair of sides in that trapezium, opposite sides equal, but there's other properties that have come along with that. These pair of angles are equal, and that those pair of angles that share a base are equal, but also we have a pair of diagonals that are equal. Now AC is equal to AB. So this is a special trapezium called an isosceles trapezium. And our isosceles trapezium has diagonals which are equal, but it also has a pair of base angles which are equal. But if we go back to our trapezium, we realize that we could have made another shape, another special quadrilateral, and that there's a special quadrilateral here, where if I drag this side in, all of these are trapeziums, but if I drag it in so that the other pair of sides becomes equal as well, well, now that's a special shape. This shape that we see here is the most important one from grade 10. This is our parallelogram. So if we think it in a hierarchical way, we can say, well, a parallelogram is a special trapezium. How did we make this parallelogram from a trapezium? Well, we made another pair of sides equal. But this parallelogram now brings a whole lot of other properties to it. So here we have a parallelogram, and we see that the opposite sides are not only parallel, but they're also equal. We see that the pairs of opposite angles are equal. None of that was true in a trapezium, but if we have both pairs of sides parallel, both pairs of opposite angles are equal. And, most importantly, in a parallelogram, the diagonals bisect each other. So all of these properties have come along. Both pairs of opposite sides are parallel and equal, the diagonals bisect, and the opposite angles are equal. So what if we had a quadrilateral that still had some properties, but it didn't have any pairs of parallel sides? It wasn't a trapezium, it wasn't a parallelogram. Well, the shape that you learnt about was the kite. The kite doesn't have any parallel sides, but the kite does have some special properties that you've learnt about. The kite has two pairs of adjacent sides equal, one pair of opposite angles are equal, the other pair is bisected, and most importantly, the diagonals are perpendicular to each other. If we have a look at our kite, we can see all those properties we've just mentioned here. But can we make a special shape out of this kite? Well, if I drag this side in so that not only one pair of adjacent sides are equal, but two pairs of adjacent sides are equal. Now we have a special kite where if all of the sides are equal, we remember that that is called a rhombus. Now if it's a kite, these diagonals are still perpendicular to each other. one pair of opposite angles are equal, but now the other pair of opposite angles are equal. Now, doesn't that property sound familiar to you? If we look at another property of this special kite that we call a rhombus, the opposite sides are equal. And this pair of opposite sides are equal. Those properties are all to do with the parallelogram. So here we have our parallelogram and all the properties that come with that. But if we think about a special parallelogram, suddenly we notice that all four sides are equal. Again, we have a rhombus. And if we notice what's happened with our diagonals, now suddenly our diagonals intersect at 90 degrees. That's not true here, but if we look at that special parallelogram called a rhombus, that is true. So, if we go back to our hierarchy, we've seen that a kite, there's a special kite called a rhombus, but that there's also a special parallelogram called a rhombus. Thus, a rhombus is like a marriage between a parallelogram and a kite. It inherits all the properties of the parallelogram and all the properties of a kite. But when we merge those two properties, we get unique properties that come out. For example, now all sides are equal. In the parallelogram, opposite sides are equal. In the kite, adjacent sides are equal. So if my opposite sides are equal and my adjacent sides are equal, then all of my sides are equal. If we look at the properties of the diagonals, here the diagonals bisect each other. In the kite, only one diagonal is bisected, but their diagonals meet at 90 degrees. If I combine those two properties, the diagonals bisect each other perpendicularly. So when you're learning about the quadrilateral hierarchy, if we want to know what properties a rhombus has, well, we just think it has everything that comes from a parallelogram and everything that comes from a kite. Now let us return to our parallelogram. Instead of trying to make the adjacent sides equal, we can see that there's another special parallelogram. There's another special parallelogram. When I have an angle of 90 degrees here, then this is a rectangle. And a rectangle has more properties than just a parallelogram. Because suddenly in this rectangle, not only do the diagonals bisect each other, but the diagonals are actually equal in length. Now that's not true in our other parallelograms. Here the diagonals bisect each other, but they're definitely not equal. Now equal diagonals, well, we've seen that before in one of our shapes. We saw that our isosceles trapezium had equal diagonals. So does that mean that we can make an isosceles trapezium into a rectangle? I think we can. So if we drag one of these points here, and we think about properties of a parallelogram that the rectangle inherits, well, a property of a parallelogram would be that the opposite sides are equal. So if I'm looking at my opposite sides of 6.5 and trying to make them equal, as soon as they're equal, we can see that that angle becomes 90 degrees. And so I have a special isosceles trapezium where I have internal angles of 90 degrees and my other pair of sides are also equal now, which means that a rectangle is a special isosceles trapezium. And what did it inherit? What does a rectangle inherit from the isosceles trapezium? Is the equal diagonals. So our rectangle can be both a special isosceles trapezium and a special parallelogram, which means it has all of the properties of an isosceles trapezium and of a parallelogram. And when we combine those properties, we get the unique property that's not true in either of these of a 90-degree interior angle. If we go and look at our rectangle a bit more closely, we can see that there's going to be a special rectangle where if I go and think about making my adjacent sides equal, that gives me a square. So a square is a special rectangle. Well, which shape had all four sides equal? Well, that's not normally true in rectangles. In rectangles, we have opposite sides equal, but there is a shape that has all four sides equal, and that shape is our rhombus. So in our rhombus, we certainly don't have a 90-degree interior angle there, but if we go and look at a special rhombus, where the angle is 90 degrees, well then that special rhombus is a square. And what properties would this square inherit from the rhombus? Well, the diagonals would now meet at 90 degrees, and all four sides are equal. So the final piece to our puzzle, the most special shape of all, is our square. And the square brings the whole family back together. The square inherits all the properties of the rectangle and the rhombus, which means it also inherits all the properties of the rectangle that came from the parallelogram and the isosceles trapezium, and the properties of the rhombus that came from the parallelogram and the kite. So the square has the most properties. So this quadrilateral hierarchy is very useful for learning the properties, because if you want to learn what the properties of a square are, well, that's the easiest, because it just has every single possible property that is in any other shape. So if you learn the properties of the kite, the parallelogram, the isosceles trapezium, those three fundamental shapes, you know the properties of all of them. The second thing that a quadrilateral hierarchy is useful for is when it comes to proving that different shapes are. Now, if we start off with the parallelogram, we can see that from a parallelogram I can go to a rhombus. So how would I go about proving that a parallelogram is also a rhombus? Well, where does the rhombus come from? It comes from a parallelogram and a kite. So the rhombus needs to inherit something from the kite that the parallelogram didn't have. For example, that the diagonals are perpendicular. So if I take a parallelogram with perpendicular diagonals, I get a rhombus. How do I prove that something is a square? Well, I need to prove that it's first a rectangle, and then it's also a rhombus. That has a 90-degree interior angle, for example, and I could prove that it's a rhombus by all four sides being equal. So then if I've got a rectangle plus a rhombus, then it must be a square. Normally what we're going to do in grade 11 analytical geometry is that we're going to start from the parallelogram and going to look at what other special shapes it can be. So the final little thing I need to remind you of is, well, how do we prove that something is a parallelogram? And you learned this last year in grade 10. There are 5 ways to prove it. The first is that the two pairs of opposite sides are parallel. Now start to think about what tool in analytical geometry you have to prove that lines are parallel. You'd need to prove that this pair of opposite sides, the gradient is the same, and this pair of opposite sides, the gradient is the same. So you're looking at doing 4 gradient calculations there. The second way to prove that a quadrilateral is a parallelogram is by proving the opposite sides equal. What tool in analytical geometry do you have to prove that opposite sides are equal? Well, the distance formula will tell you about opposite sides being equal. You'd have to do 4 distance formula calculations. You'd have to say that pair of sides is equal in length and that pair of sides is equal in length. Another way to prove that something is a parallelogram is to prove that opposite angles are equal. What tool do you have in analytical geometry to prove opposite angles? Well, the only way you could really do it is the angle of inclination, and that sounds like it's going to be a lot of work. Now, the fourth way to prove that a quadrilateral is a parallelogram is by showing that the diagonals bisect each other. How do I show the diagonals bisect each other? Well, the midpoint would tell me if I can show the midpoint of the one diagonal has the same coordinates as the midpoint of the other diagonal, then the diagonals will bisect each other. Now think about that. That's only 2 calculations. The midpoint of the one diagonal and the midpoint of the other diagonal. The final way you learn to show that something's a parallelogram is one pair of sides is parallel and equal. So if I was to do that in grade 11 analytical geometry, I'd need to do 2 distance formulas to show that the sides were equal, and 2 gradient formulas to show that the same pair of sides are parallel. So what we can see from all of this is that showing the diagonals bisect by doing midpoint twice is by far the most efficient way to show that something is a parallelogram. And once I know it's a parallelogram, then I can look at proving what other shape it might be as well. Okay, let's go and look at some examples